we're going to do a share where we can see what it is that I am lecturing about, so to speak. So we're going to be looking at Bohr's model of the hydrogen atom. So Bohr's model of the hydrogen atom was actually built out of a lot of different information. So the first thing, well, can you see what I'm writing there?
Yeah.
Okay, great. So the first thing I'll tell you about Bohr's hydrogen atom is this model also applies to other atoms, but it is specific for the hydrogen atom. And the reason, of course, that you study the hydrogen atom is because it is the simplest atom. 99.99% of the hydrogen atoms have exactly one proton and one electron. So that means the electron can only be affected by the proton and vice versa. There's no neutron to get in the way. There's no other electron to get in the way. There's no other proton to get in the way. Okay. So it is the simplest system that you can study and build a model out of. And a lot of study was being done on at this time. So for instance, you know the emission spectrum of hydrogen, where you can see three visible lines, or excuse me, four visible lines. A guy named Rydberg came up with an equation where if you used n equal 1, if you use n equal 3, n equal 4, and so forth, all the way up to 5, you would actually calculate the wavelength of each of those lines. And so it's kind of interesting. He came up with an equation that predicted that you would get those wavelengths, but he had no reasoning behind it. He just said, hey, the equation works. But he had some information on how to get there. Well, Bohr obviously saw this information and kind of built this model out of that information and other things. But his model is very simple, that you have a proton with an electron that is orbiting the nucleus, just like the planets orbit the sun. Only in his case, the orbits would be perfectly spherical. They would not be elliptical. He did not try to explain why the electron would not be sucked into the nucleus because of opposite charges are attractive, right? Mm-hmm. So he had no explanation for why the electron would actually stay out there. And he also said that the electron could orbit at different levels, different distances from the nucleus. It did not have to be at a particular, I could say it did not have to be at one distance. It could be at several different distances. But the interesting thing was it had to be at specific distances. It couldn't be in between. So imagine, if you will, that you could only be a certain distance from the wall, but never in between those two distances. That's what he was saying. No explanation for that either. His model predicted the energy of an electron in one of those orbits. And the energy of the electron in one of those orbits goes as follows. E is equal to negative RHC over n squared, where you already know that R is Rydberg's constant. And Rydberg's constant comes from that one equation where the guy, Rydberg, invented an equation where you could actually predict those four wavelengths in the visible spectrum. H is Planck's constant. And Planck got his constant from developing that formula for the energy of light compared to its frequency. And C is the speed of light. And N is the orbit. So the orbits were given values of 1, 2, 3, 4, and so forth. So you could be in the first orbit, the second orbit, the third orbit, or the fourth orbit. Now, let me give you a little explanation as to why this is negative, okay? So I want you to imagine that you have your proton right here, and here's your electron, orbiting the nucleus. So I'll even put a little arrow in here because it's orbiting the nucleus. Are you with me?
Yeah.
Okay. Now there's an attraction here. Due to charge attraction. Opposite things are attracted to one another, okay? So I want you to imagine if we do something like this, if we take that electron and we remove the electron away from the proton, are we going to have to put energy in or will this give off energy?
Put energy in.
That kind of makes sense, right? Because these things are attracted to one another. So you literally have to pull the electron away, which means you have to add energy to the system, if you will.
Right.
So this is considered to be endothermic with a positive value. Now, we learned from the previous chapter, what happens if an electron comes from outer space and ends up right there? What will happen? Will energy be absorbed or will energy be released?
Released.
Right. So here it's absorbed and over here it's released. Now, when it's released, we call that exothermic. And what is the sign on exothermic?
Negative.
Negative. And so that's why this value is negative. It's basically the energy that is released by an electron coming from outer space and ending up on an atom. Are you with me there?
Yeah.
Now I want you to take a look at this here. So here's my proton. Here's n equal 1. Here's n equal 2. Here's n equal 3. So this electron is coming from infinity. It's coming from a great distance away. When it ends up here and n equal 1 versus here n equal 2 versus here n equal 3, which one of these events will release the most amount of energy?
Getting to n equals 1.
Correct. So this is going to be the greatest energy. And this will be the least amount of energy released. So the point here is that we have different energies for the electron based on which orbit it ends up in. And if you look at that equation again, we can see that when we plug a 1 in here, you have this value up here, which is basically, it's a constant. It doesn't change because R is a constant, H is a constant, and C is a constant. So when you take this value and divide by 1 squared versus 2 squared versus 3 squared, the bigger n is, the smaller this amount of energy is. So we can actually see that in the equation that the orbits are essentially bigger and bigger and bigger. Or if you're looking at 3 down to 1, smaller and smaller and smaller. But still, it's kind of interesting that you can't end up in orbit 2.5. The electron cannot end up halfway.
Yeah.
And this is the explanation for why you get those lines. So for instance, why do you get a line in an emission spectrum? What can actually happen is, and so I'm going to show you another image. And what I'm going to do here is I'm going to do n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, and here is the nucleus. So what I'm doing now is I'm kind of taking the hydrogen atom model and I'm just applying it to any atom whatsoever with orbits. Okay? So those visible lines in the hydrogen spectrum are due to this energy change from 3 to 2, 4 to 2, 5 to 2, and 6 to 2. those result in those 4 colored lines.
Why only to 2?
Well, because the ones that end up in 1 are ultraviolet, and the ones that end up in 3 are infrared.
Okay.
So these, I'm going to put a little V next to these. These are visible. This one, if you go from 2 to 1, is ultraviolet. If you go from 3 to 1, it's going to be ultraviolet. If you go from 4 to 1, it's going to be ultraviolet.
So we can't
So
see.
when I say that the ones that end up in 2 are the visible lines, those aren't all the lines, they're just the visible ones.
I see.
Okay? It's a good question why, why only 4? It just so happens that when they end up in 2, they're visible,
Okay.
and so forth and so on. And remember how we talked about the spectrum where ultraviolet is more energy than visible, visible is more energy than infrared?
Yeah.
So the lower you go down on this chart, the more strong the radiation is going to be. Electromagnetic radiation, that is.
Mm-hmm.
Okay, so that's how I know that, these are visible. And here, if you go from like 4 to 3 or 5 to 3, that's going to be infrared. A little less energy because you're not dropping as far down. Okay. All right. So now when you look at this whole concept here, which I'm going to now make a little simpler so that we can focus just on this, n equal 1 and n equal 2. And we look at this electron going from here to here. This is, I want to remind you, exothermic. The sign is negative and energy is released. Now, when energy is released, you're going to see that energy as a wavelength of electromagnetic radiation. So there are 2 things we have to do. We have to first calculate the energy change here, and then we have to calculate the wavelength associated with that energy change. So I'm going to show you how you get that equation for finding the change in energy. So the change in energy is equal to the energy of the final state minus the energy of the initial state. So we're used to seeing that now, where delta is final minus initial. If we look at this final state, it's n equal 1, right? So that's negative RHC over n final squared minus negative RHC over n initial squared. I'm going to put that all in big old parentheses for no particular reason. And then I like to write this formula as follows. Negative RHC 1 over n final squared minus 1 over n initial squared. So I factor out the negative and the R and the H and the C. So I get this. Now, when you multiply negative R, H, and C together, you get like 2.178 times 10 to the, maybe it's 2.0178. Well, let's find. Pardon me?
Can you repeat what you're doing?
What I'm doing here is I'm multiplying R, H, and C in my head and trying to remember the value.
Okay.
So R is 1.0974 times 10 to the 7th. H is 6.626 times 10 to the minus 34. And C is 2.998 times 10 to the 8. I didn't do it right. Okay, it's 1.0974 times 10 to the 8, I think, for Rydberg's constant. So you get 2.180.
Negative?
So I was pretty close. Times 10 to the minus 19. And the units are going to be joules when you look at all of that stuff multiplied together.
How come I got to the negative 18?
Because you used 1.0974 times 10 to the 7th, and I think it's times 10 to the 8th. What is Rydberg's? Is it 10 to the 7 or 10 to the 8th?
I have it written down in 3 separate places as 10 to the 7th.
Okay, then this should be 18 then.
Okay, good.
Okay. So this is one of those things that'll actually help you with doing the lab, knowing that number.
Okay.
Okay, so you'll notice here I forgot my little squareds here, but I just added them in. So let's calculate the energy change for going from 2 to 1. So change in energy, and I'm going to put 2 to 1 here so that we know we're going from 2 to 1.
Okay.
And that's going to be negative 2.178 or 180 times 10 to the minus 18 joules times 1 over 1 squared minus 1 over 2 squared. And you know that 1 over 2 squared is 1/4, right? And 1 over 1 is 1. So this is basically going to be 0.75 times this value. So it should be about 1.5 times 10 to the minus 18 or something like that.
Okay.
And it's 1.635 times 10 to the minus 18 joules. And that's a negative. So this is one of those instances, again, where with the algebra, it's easier to clump things together that are easier to deal with, like the negative RHC.
Right.
So if you look at the original equation here, you know, rather than do negative RHC here and then divide it by n final squared and then do negative RHC here and then keep track of the sign, it's easier to kind of compartmentalize these things, or, you know, get everything grouped together in easy to handle bundles.
Now, can we keep that negative RHC value for our exam and just plug that in?
Yeah, I mean, if you have to use this equation and you have that on your note card, you don't need to calculate it again and again and again.
Okay.
I mean, it's a perfect example of a good use of your note card, in my opinion. Because if there's one place where people tend to make mistakes on their exams without meaning to, it's using their calculator.
Yeah.
Okay, now look at this negative sign. That correlates to a wavelength. So how do we calculate the wavelength? Well, remember, E is equal to hc over lambda.
Yeah.
So here, that means lambda is equal to hc over E.
And I was wondering, when do we use E equals, is it HC?
No, it's h nu.
H nu versus E equals HC over lambda.
And the answer is you use E equals h nu when you have nu. You use E equals hc over lambda when you have lambda, or when you want lambda, or when you want nu.
Okay.
So you just use the one that you want. And since we're trying to calculate the wavelength, we're going to use this top one rather than this bottom one. If the question was, what's the frequency? I'd use this one.
Right.
So that's the only reason why you use one or the other, depending on what you're being asked. And more often than not, since we're looking at emission spectra and we're looking at wavelengths of lines, you want wavelength, not the frequency.
Okay.
And mostly that's because you can see wavelength, you can't see frequency. Okay, so here we've got, now I want you to notice something here. Take a look at this wavelength equation. And this is based on the energy. If I put energy as a negative value, my wavelength is going to become negative, right?
Yeah.
What does that negative mean for wavelength?
That it's energy being released.
Right. So wavelength being, we don't use the word released, emitted.
Emitted.
So that's a wavelength you're going to see.
Okay.
So we'll go ahead and leave the negative in there. I normally don't, but I'm beginning to like the idea of having negative wavelengths because that means those are wavelengths you are receiving. They're emitted. And a positive wavelength would be one that's being absorbed. Does that make any sense?
Yeah.
So I don't, I'm not bothered by having negative wavelengths. It's just like energy. There's no real such thing as negative or positive energy. It's just whether it's coming or going.
Right.
Okay, so let's calculate this value. H is 6.626 second EE negative 34 times 2.998 second EE 8, and then divided by that 1.635 second EE negative 18. And so we get 1.215 times 10 to the minus 9, and that's going to be meters.
Or a nano.
Oh, well, I'm sorry, 7.
So this is the wavelength of an electron going from N2 to N1.
It's the wavelength of light emitted when an electron goes from N equal 2 to N equal 1.
Okay.
Okay, so if we go back to this drawing here, we see that this is exothermic, energy is released. And some people actually do this. You go, boop, there's your energy being released, right?
Mm-hmm.
That energy results in a wavelength of light that you can see.
Okay.
Well, I should say you can detect. And we're going to see why you can't see this one in just a moment. So negative 1.215 times 10 to the minus 7 meters, we multiply by 1 nanometer over 1 times 10 to the minus 9 meters, we will end up getting 1.215 times 10 squared, which will be 121.5 nanometers. Now, is that within the realm of visible light?
No.
No, it's a little too short, right?
Yeah.
And since it's shorter, that means it's stronger than visible light, right?
Yeah.
And what is that thing that's stronger than visible light, but right next to it?
Is it UV?
Correct. So that's UV light.
Right.
Okay, so let's see how when you end up in the second orbit, it does end up being visible light, okay?
Okay.
So let's do this change in energy from 3 to 2. And if this were an exam question where you're being asked, calculate the change in energy for 3 to 2, and what wavelength of light is this, and what part of the spectrum is it in? Just like we did for the previous one, how would we set this up? So the way I would start is negative RHC 1 over n final squared minus 1 over n initial squared. Then what will we do next? Probably negative 2.178 times 10 to the minus 18 joules times 1 over, which one is final, 3 or 2 based on what I've written here?
2.
Okay. Okay, now see how this is nice and compartmentalized? I'm going to do 1 divided by 2 minus 1 divided by 3 first. And my idea here is that 1 divided by 2 is 0.5, or excuse me, 0.25, because that's 1/4, right? And 1 divided by 3 squared is like 0.1, so I should have around 0.15-ish for the difference, right?
Right.
And I know that 1 over 3 squared is not 1 over 10, so it's not 0.1. It's more than 0.1. So here I expect this to be a little smaller than 0.15. So let's see what we get for that. And I get 0.11. Is that what you get?
I don't know, I'm slow. 0.11? Yeah.
0.11.
Yeah. So that's joules.
Well, actually, I made a mistake. Let me make sure I'm doing this correctly.
Yeah, it's not as small as.
It's not 0.11, it's 0.138.
Would you do different?
0.139.
How'd you get that?
Okay, so in your calculator, put clear,
Mhm.
put 1 divided by 4,
Mhm.
then put minus 1 divided by 9,
Mhm.
and then put equal.
Oh.
So what I'm doing there is I'm relying on the calculator doing the order of operation. So when I say 1 divided by 4, I'm just saying screw 2 times 2. I can do that in my head.
Mhm.
So I'm doing 1 divided by 4.
Yeah.
And then I want to put minus 1 divided by 9. My calculator does the 1 divided by 4 first, the 1 divided by 9 second, then subtracts the 2. Okay, so now I'm going to multiply that times this negative 2.178. Or 2.180. I keep making that mistake.
I was wondering.
It's actually 2.1799 something, but you know, when you're round, it's 8. And our numbers should come out to be smaller than the first value we calculated, which was 1.6 times 10 to the minus 18.
Right.
Now this is a negative, and I get 3.028 times 10 to the negative 19 joules. Is that what you got?
Yeah.
Okay. Now this has 4 significant figures because of this. And the reason this has 4 significant figures is because this 1 over 2 squared, the 2 is exact. 1 over 3 squared, the 1 is exact. So this has infinity significant figures. This has infinity significant figures. And therefore the difference has infinity significant figures. So that's another thing that you might want to put into your data bank, is that, hey, the number of significant figures in this calculation is limited to what I have in front here. And what we had in front here, we used the speed of light, which was 2.998, 4 significant figures.
Yeah.
H, 6.626, 4 significant figures. R had 5 significant figures, so you get 4 there. Okay?
Yep.
All right, so that's the change in energy. What's the wavelength going to be equal to?
So we have, oh, you already wrote that down.
Yep, but you're supposed to think through it. Normally you would think E equals H nu, but also E is equal to HC over lambda.
Right.
And you get HC over lambda because nu is C over lambda.
Yeah.
They are the same thing.
Okay.
So when you plug values in here, what do you get? 6.626 times 10 to the minus 34 joule seconds. 2.998 times 10 to the 8th meters per second. And negative 3.028 times 10 to the minus 19 joules. So with my calculator, what I did immediately is I took that answer I had the first time and I took the inverse of that.
Okay.
And then I'm just going to multiply by 6.626. Second, EE negative 34. And then times 2.998, second, EE 8. And I'm going to put that in scientific notation, and I get 6.561 times 10 to the negative 7 nanometers. Oh, I'm sorry, meters. I'm thinking ahead to, we need to put this into nanometers so we know where it belongs on the spectrum, right?
Yeah, I have a question though. Why is it 0.561? Because on my calculator, I have a 3 next to the 0.
I have a 5 next to it.
Oh, okay.
I mean, I have an 8 next to it, not a 3. I have 0.65608. Let me ask you, this negative 3.028, did you use this value or did you use the value you got before rounding?
I used our rounded value.
Okay, see, I didn't, and that's may have made a difference.
Okay.
And that's why they say you don't round till you're all the way done. So that's not a big deal, that last number. Now, what does the negative sign mean for this wavelength?
It is emitted.
It's emitted. Normally, when you do this calculation, you just use the energy value. You don't use a negative because we understand it's emitted light. When you go from a high level to a low level, it's exothermic and you're emitting light. But you know, as long as we're talking about it, what happens if you do the opposite? You go from a low level to a high level.
You put in energy.
Right. And it takes a specific amount of energy to do that. Not just any energy, a specific amount. So to get that to happen, you basically have to shine a light at something and it absorbs that energy. But like if you shine visible light at a hydrogen atom, you're not going to get something to go from the first level to the second level because there's not enough energy there.
Okay.
It has to be ultraviolet light, right?
Yeah.
So ultraviolet light is not going to get you to go from 2 to 3. But visible light presumably might be enough light to get you to go from 3 to 4, which is infrared, because there's more than enough energy there. Okay. All right. So how do we find out that this is in the visible spectrum?
Convert it to nanometers.
Okay, so I'm going to show you another way to do this. Are you ready?
Sure.
Okay, I'm going to multiply by 10 to the 9th by 10 to the minus 9th meters. So what happens when I multiply by 10 to the 9th times 10 to the minus 9?
Don't they cancel?
They cancel. They don't really cancel, but they become 10 to the 0, which is 1. So I'm multiplying by 1, correct?
Yeah.
So now I've got 6.561 times 10 to the minus 7 times 10 to the positive 9 times nanometers. So I've taken this 10 to the minus 9 and I've turned that into a nano. Is that okay?
Yeah.
Okay. So what's 10 to the minus 9 times 10 to the 7?
10 to the 2.
Actually, I said that the reverse of what I should have said. What's 10 to the minus 7 times 10 to the positive 9?
Positive 2. 10 to the
Okay.
positive 2.
Or 100, right?
Yeah.
What's 100 times 6.561?
656.1.
Okay. So what region of the spectrum is that in?
Visible light.
And how do you know it's visible light? Because you've memorized that visible light goes from where to where?
400 to 700.
There you go. So when we go from 3 to 2, that's going to be a visible wavelength. Now, let me show you something from the book. Okay, so this is the from the book. I don't think these colors are necessarily correct, but do you see here this 656.3?
Mm-hmm.
Okay, and they're going from 3 to 2, and that's in the red part of the spectrum, which we know it should be, right? Because it goes vid-Gyr, R is near 700.
Yeah.
So what do you think about this calculation? Is it something that represents what we should get?
Yeah. Seems pretty accurate.
Yeah, so that's how you calculate the energy that is being emitted or the energy being absorbed.
Okay.
And that's what Bohr's equation is really good for. So when you're first introduced to the equation as simply E of n is negative RHC over n squared, that is the energy in the nth orbit, whatever orbit you're talking about. And if you do that calculation for two different orbits and subtract them, you're going to get the total change in energy. And that's another way you could do it, is you could do that, and then you could do that and subtract the two. But usually I find there's more room for error there.
Yeah.
Okay, so that's Bohr's atom. And that's kind of what I did not want to discuss the last time we met, because we talked so much about wavelength and other things that this is like an added, oh my God.
Yeah.
But this is a pivotal part of this chapter, a huge part of this chapter, being able to work with Bohr's model.
Okay.
Okay.
I have another kind of question about how the joule with the particle wave duality, where a joule is a kilogram times meter squared over second
Yeah,
squared.
that's something that we don't tell you until now.
Uh-huh.
A joule is actually a complex unit.
Okay.
And here, when you look at the wave particle duality, so you're looking at what is the name of that guy? DeBroglie. You're looking at the DeBroglie wave equation, right?
Yeah.
Okay, so the reason this is important is that we have to back it up to the concept of light. The first model was light is a wave, right?
Mm-hmm.
And the second model was light are these massless packets of energy called photons. And it's natural to think of a packet as a particle, but these things don't have mass. So de Broglie, along with some other information at the time, thought, well, let's flip the coin. is it possible particles can be treated as waves? For instance, you running down the street, do you give off a wave? So could we treat particles as if they are waves? And that's what this duality part is. So the idea here is that you can relate, hopefully, the wavelength of an object to some information. And so you get DeBroglie's wave equation, which is the wavelength is what? HC over, no.
H over mv.
Over mv.
Mass and velocity.
Okay, so what is m and what is v?
Mass,
And what is v?
velocity.
Good. Now, to use this equation, it's important to understand a few things. So let's take a look. For h, it's joule seconds, right? So I'm just going to write this in terms of units, joule seconds.
Okay.
And I'm going to leave these on the bottom alone for right now, okay? Now, when we're done with this equation, what type of unit do we expect?
Meters.
Meters. Okay, so here we know that this should be meters. And what is the most common mass that we use? Well, actually, I'm just going to give it away. It's grams, but in this case, the mass must be in kilograms.
Right.
Now, for the velocity, we usually use miles per hour when we're driving our car, right? But in Canada, they don't. They use kilometers per hour. Here, we use meters per second. Okay, so these are the units for velocity. These are the units for mass. Let's figure out what the units are for a joule. So how are we going to get joule on one side and everything else on the other side?
Multiply by the denominator.
I would cross multiply first. So I would have joule seconds is equal to kilograms meters per second times meters.
Where do you get? Oh, I see. Okay.
So basically, I'm putting the m over 1, and I'm doing joule second time 1, kilogram meters per second times meters.
Okay.
Okay. Now what am I going to do to this to get joules alone?
Divide by seconds.
Divide by seconds.
Um,
And here, let's go ahead and combine these 2 meters and call it meters squared. So these will cancel and we get joules, and you find out that a joule is a kilogram meter squared per second squared. So you can see that joule is a complex unit. Now let me explain to you why it is this unit. This is a physics explanation. So this is really a kilogram times a meter per second squared. That's what this really is. Okay, so why does energy depend on mass? Why does energy depend on distance? And why does energy depend on meter per second squared, which is called acceleration? So why does energy depend on the mass, the distance, and the acceleration? So I want you to imagine a frictionless space. So that means like when you, let's a frictionless track. So if you push a car on the frictionless track, it will travel on that track forever at the same speed.
Forever?
Forever. So frictionless track means there's no air friction, there's no friction with the track. You just push it and it goes forever. Okay. That doesn't happen because air does have stuff in it that slows things down, but we're talking about a totally frictionless system. So if you push something down the track and then you let go and put no more energy into it, it goes forever. How much energy do you have to put into it for it to go forever? And the answer is 0 energy. Okay. Now I want you to imagine that you want to speed it up. In other words, you want to accelerate it. So let's say it's going 1 mile per hour and you will now want it to go 2 miles per hour. Are you going to have to put energy in to increase its speed to go 2 miles per hour? The answer is yes. Will that depend on how much you want to get it to speed up?
Yeah.
Will it take more energy to make it go 2 miles per hour or 3 miles per hour, or does it not matter?
It takes more the faster.
So here, that's why acceleration is part of the energy, because it takes more energy to accelerate something greater. Now, when you're accelerating something, trying to get it to go faster, doesn't matter how much distance you have to put into that acceleration. Like if you accelerate something for 1 meter of push versus 2 meters of push, is that the same amount of energy? Is it different, or does it not matter?
It's different. The greater
So,
the distance, the greater
right,
the-
and so that's why you have the meter. And imagine you're pushing your niece versus your son, and you're trying to accelerate them both to the same speed. Are you going to have to put more effort into accelerating your niece or your son?
The larger child.
The larger child. Is your son larger?
No.
Okay, but that's why Joule is made out of these different units, because it depends on mass, it depends on length of acceleration, and it depends on the acceleration itself. And so this is just a try to help you understand why Joule is a complex unit.
Okay.
Okay, so here, if we go back to the de Broglie wave equation, you can see that here, if we have joules, seconds, kilograms, and meters per second, and then we substitute kilogram meter squared per second squared for joule second over kilogram meters per second. Can you see how this second cancels with one of these? So I'm going to cross the 2 off. This second is in the denominator, right?
Yeah.
This second is in the denominator, so they both cancel. This kilogram is in the numerator up here, and it's in the numerator up here, so they cancel. This meter's in the numerator, and so is this one, but there's 2 here, and there's only 1 here, so only one of them cancel. So what is our unit going to be when we're done here, as long as we use kilograms for the mass and meters per second for the velocity?
Meters.
It's going to be meters. So this is something that's hugely important for you to use this equation. If you're given a mass in grams, convert it to kilograms. If you're given a velocity in miles per hour, which you're normally not, you're given in meters per second, convert it to meters per second. So let's do something that's really weird. Let's calculate the wavelength of an Olympic sprinter. So you know these Olympic sprinters, they run the 100-meter dash, not the 100-yard. It's the Olympic standard is a 100-meter dash. You with me?
Yeah.
And there's a guy named Usain Bolt who's really fast, and I believe he runs like a 9.6 second 100-meter dash. It's under 10. It may be 9.7, but I think it's like 9.6. He's really fast. So what wavelength does he give off? Well, we have to first find out, how much does an Olympic sprinter weigh?
Right.
And the answer is about 100 or I won't say 100 kilograms. It's more like 80 or 90 kilograms. So about 200 pounds.
Okay.
So let's use 80 kilograms for their mass. And how fast are they running?
You said 9.6 meters per second.
Not per second, 9.6 meters in a 100-meter dash.
Right.
So we're going to use 6.626 times 10 to the minus 34 joule seconds. We're going to use 80 point kilograms and pretend that they're two significant figures on the mass, okay?
Okay.
And for the speed, we're going to use 9.6, oh, excuse me, 100 meters over 9.6 seconds. Does that sound like a velocity?
Yeah.
Okay. So let's find out what sort of wavelength this gentleman has. When you're done, you tell me what you get.
I got 8.6. Is that, I don't know if I put that in my calculator right.
Well, let's estimate the answer before you do that. How's that sound real quick? How many times does 9.6 go into 100?
About 10.
10. What's 10 times 80?
800.
Okay, isn't 800 0.8 times 10 to the third?
Yeah.
Okay, how many times does 0.8 go into 6.6? How about this? How many times does 8 go into 66?
Oh, is that about 8?
About 8 times. Okay, good. What's 10 to the third into 10 to the minus 34?
Minus 31.
Nope, minus 37 because this is on the bottom.
Yeah.
You put it on top, you got to change the sign. So you should get 8.0 times 10 to the negative 37. And what are the units going to be since we made sure we had meters per second and kilograms?
Meters.
Meters. So let's talk about this wavelength. Is this a long wavelength or a short wavelength?
Short.
So what does that mean for frequency?
It's strong. Or
High. We
high.
like to use high. What type of energy is this? High energy or low?
High.
And this energy is a lot higher than any gamma ray, any X-ray, any visible light. This is a huge amount of energy. So what does that tell you about the energy of one photon compared to a gentleman running down the track at 9.6 seconds for 100 meters?
Very small.
Very small indeed. Very small indeed. There's more energy in one person than there is in millions and millions of photons, billions of photons. Okay, that's why you don't want to get run over by a person, much less a truck.
Yeah.
Okay, so this is kind of an interesting exercise. Does this have any meaning to us that, you know, hey, this person's giving off this wavelength? Maybe you use this for a traffic ticket. You say, well, you know what? I was accelerating to the light. And so there was a red shift that made the light look green. That's why I ran the light. It looked green to me, officer. It's not going to fly here, right? Because this is clearly not in the visible area.
Right.
And probably the officers have been trained in this now to say, well, you know what? That's not in the visible region, so it doesn't work. And you go, darn. Okay, so where does this apply? It applies for electrons, which is what we were talking about before, right?
Yeah.
So this is applicable to electrons moving. They might give you a wavelength of light that is measurable, if you will. Okay, so there is a problem in the book if you want to look at it. I think I do it as an example. But they talk about, I believe they ask about a wavelength of an electron. Here we go. The rest of these are rather silly. 2 of these are good and 2 are silly. So do you see the silly ones?
What makes them silly?
What is the wavelength in nanometers associated with a golf ball? That's silly. I mean, come on. A rifle bullet. That's silly. An Olympic sprinter. That's silly. But how about this? An electron with a velocity of 2.5 times 10 to the 8 centimeters per second. And what is its wavelength? And a beam of electrons. So let's do number 23. An electron that moves with a velocity of 2.5 times 10 to the 8th centimeters per second. So we've got an electron where the velocity is 2.5 times 10 to the 8th centimeters per second. And we're going to use the wave equation. So what are we going to have to find out here to be able to do this that we're not given?
The mass?
Mass of an electron. Now the mass of an electron is 9.01 or something like that. Let me look it up real quick. This is way back in, I think, chapter 3, when they talk about subatomic particles.
Yeah. Is this
And I want to say it's 9.0 essentially times 10 to the minus 28 grams.
Is this something we need to know?
No, I would give something like that to you because that's, I told you that you should know that an electron weighs 0. Do you remember that?
Yeah.
Because I wanted you to have a better idea of how much it weighs compared to a proton.
Number 24, I think, gives the mass of an electron.
Oh, what does it give?
9.11 times 10 to the negative 31 kilograms.
Okay, I'm going to change that.
Why? So we want kilograms?
We do, but I'm going to change that because earlier in the book, they give us 9.11 times 10 to the minus 28 grams. So I wasn't too far off. My guess was 9.01.
Okay.
So the reason I'm doing this is because I want you to do a little more work to get the answer.
Okay.
So how do you change that into kilograms?
Multiply it by 1 kilogram,
Over.
1,000 grams.
Okay, and what do you get?
9.11 times 10 to the negative 25.
No, this is 10 to the third on the bottom.
Yeah.
When you move it on top, it becomes 10 to the minus 3.
Okay.
So what does minus 3 and negative 28 add up to?
Minus 31.
Right. So that's twice you've done this now. Let's not do it again because third time you're out.
Okay.
What do you want to do with the velocity?
Change it to meters per second.
Okay. How are you going to do that?
Quietly.
I'm going to multiply by 1 meter over 100 centimeters, I'm sorry.
Yeah.
Because I happen to know, I remember when the teacher pulled out the meter stick and they said, there's 100 centimeters in here. I don't know why, but I remember the guy doing that and saying, yeah, there's a, and moving his arms. I remember that from when I was a kid.
Right.
So I'm going to do that. And that means it's 2.5 times 10 to the 6 meters per second. So now we can put it all together and see what you get. Before you plug it into your calculator, I want you to try to make an estimate.
Okay.
Then after you get your estimate, give it a try and see if you get close to your estimate.
All I've estimated so far is the power on the 10.
And what did you estimate on the power on the 10?
Is it -9?
That's what I would go with also, because 6 and -31 is -25. When you bring the 25 up, it becomes +25. +25 and -34 would be -9.
Okay.
How many times does 2.5 go into 6.6?
A little more than 2,
A little more than 2?
right?
Yep. Almost 3, right?
Yeah.
So between 2 and 3. How many times does 9 go into 3?
0.303.
Yeah, 0.3, right?
Yeah.
Okay, so 0.3 times 10 to the minus 9 makes it 3 times 10 to the minus 10, doesn't it?
Yeah. I think so.
So let's see what you get by putting it into your calculator.
Um, 2.9 to the negative times 10 to the -10
And what are the units here?
meters,
Meters. And how do we know they're meters?
because we have the right units.
Because we made darn sure that we have kilograms and meters per second. That's why. And we went through the whole exercise of knowing that we need to do that, because a joule is a kilogram meter squared per second squared. Right?
Yeah.
So hopefully that little background gives you the little extra juice, if you will, to understand why you need to have kilograms and why you need to have meters per second. And maybe a better, kind of a little bit of a better understanding of what an energy unit actually is comprised of.
Yeah.
So that's pretty interesting. The calorie, on the other hand, was not thought of that way. It was just thought of the amount of energy needed to heat a gram of water by 1 degree Celsius.
Yeah.
The joule, they actually thought, okay, the joule is based off of the idea of trying to accelerate something. What are the things that will make the energy required greater? And the mass of the object, clearly that's going to influence it. How long you accelerate it for, and how fast you accelerate it. It's kind of like, you could think about it almost like a car. What are the things that are going to matter for the amount of energy to accelerate a car? 1, how big is the car? 2, how much are you going to accelerate? Are you going to accelerate it for a quarter mile, or are you going to accelerate it for 1/8 of a mile? And how fast are you going to accelerate it?
Right.
So I don't think it was a car enthusiast that came up with the joule. Maybe it was a horse enthusiast. What matters when you accelerate a horse? Size of the horse, I don't know. But it's pretty interesting stuff. Physics is a really outside of my reach, but that's one of the things of physics that I find kind of interesting.
Yeah.
Okay, I think we've done a pretty good show here. You've learned how to use Bohr's equation to calculate the energy of an electron in an orbit. You've learned how to calculate the change in energy from one orbit to another. You've learned how to calculate a wavelength associated with that change. You've learned how to calculate the wavelength of a particle, right?
Right.
So you've done quite a bit here. And the rest of the chapter is weird. It's quantum mechanics. I call it magic.
Yeah, yeah.
But there are certain things that you just want to know about quantum mechanics. And a lot of it is memorization.
Right. With the shells, you talk about the shells and the subshells and N and L and N
Yeah.
sub L.
Shells, subshells, and orbitals. Oh my.
Yeah.
It's really, I will give you this little introduction into the model.
Yeah.
The model is based on Schrodinger's model of the hydrogen atom. And do you remember how we just said, well, maybe we can treat particles as if they're waves?
Yeah.
Schrodinger said, let's treat electrons around an atom as if they were waves. Not particles, but waves. But they have to be something called a standing wave. Do you know what a standing wave is?
No.
So here's the best way to describe it. Imagine, if you will, a guitar string. When you pluck a guitar string and you take a film of the guitar string moving, what it looks like is there's a bunch of places evenly spaced on the guitar string that don't move. In between those 2 points, what you see is what looks like a little hill or a little hollow that goes up and down. So that's the string vibrating. The places where it doesn't seem to move are called nodes. The place where it does move, that's where you get the sound from. So depending on how close the nodes are together, you get different frequencies of sound. So you get the deeper sounds and the higher pitch sounds. You with me?
Yeah.
So that's a standing wave. So basically, DeBroglie thought, not DeBroglie, but Schrodinger said, well, let's treat the electrons around a nucleus. So here's your nucleus. It has standing waves. So, this is what a standing wave looks like, where at this part, it goes up and down, up and down, up and down. You with me?
Mhm.
So here he said, well, we're going to make these standing waves. Now, for them to be standing waves, this is perfect. You see how it comes back to itself?
Yeah.
But this one, I'm making this happen the way I want it to be honest with you. Well, but this one, you see, it doesn't quite work. They don't meet where they should. You with me?
Mm-hmm.
So this does not work for an electron. And the reason is it's not a standing wave. This is a standing wave. So with this in mind, only certain standing waves are going to work for your atom. And those standing waves correspond to the orbits of Bohr's hydrogen atom. So whereas Bohr just said, well, the electron has to be a specific distance from the atom or from the nucleus, and I'm not going to tell you why because I don't know why.
Yeah.
Schrodinger said the reason these electrons have a specific energy, because these are waves translated to energy, right?
Yeah.
So the reason these electrons have specific energies is because they are standing waves, not just any kind of wave, they're standing waves.
Okay. So that's why L and M sub L has rules.
That's why you have those little rules, because the equation for a standing wave is called a wave equation.
Yeah.
And this is the symbol for your wave equation.
Yeah.
and you know how you have Cartesian coordinates of X, Y, and Z?
Sure.
Well, you know about regular coordinates are of X and Y, right?
Yeah.
When you add the third dimension, it's X, Y, and Z.
Yeah.
These waves are actually three-dimensional things, so it depends on three things, N, L, and M sub L instead of X, Y, and Z.
Right.
And because they are standing waves, you can't have just any value of any combination of N, L, and M sub L. You only get specific combinations because they're standing waves.
Okay.
So that's why you need to know the rules for those things.
Right.
Now, you can probably guess what N stands for. The orbit, as it were, in Bohr's atom.
Mm-hmm.
L is called the angular momentum, and M sub L is the magnetic quantum number.
Right.
And there's two big things you need to understand about this equation. This gives you the energy. This gives you the location. So this pitchfork is called psi. Psi gives you the energy. Psi squared gives you the location. And when I say energy, energy of what?
The electron.
Correct. And so location would be location of the
Electron.
Now, when I say location, the reason I have air quotes here is because it's not the real place you're going to find the electron. It's where you're likely to find it.
Yeah.
Like for me, I tell you that you'd be likely to find me in Eureka. Would that help you find me exactly? Nope, because it's a big place. So this helps you find where the electron is going to be, but not exactly where it is. So that means that usually for these wave equation solutions, we get a sphere around the nucleus saying, in all probability, you're going to find the electron in this region. And sometimes the regions have different shapes depending on M sub L.
That's
So
the plot.
yeah, those probability plots are the locations.
Yeah.
And the stuff we're getting into there, the quantum mechanics we're getting into, is not even the tip of the iceberg. It's like nothing. This is like so introductory that most physicists would say, oh yeah, you're talking quantum mechanics. And we're not really. We're just introducing a snippet of the idea. It's far more complex, and a lot of physicists do this stuff and they have no problems with it. But the conceptual stuff I like, the calculations I don't.
Yeah.
We're not doing any calculations. We're just memorizing what are the allowed values of this for a standing wave.
Right.
That's what we're doing. And for those values, what does it tell us about where you're going to find the electron?
Right.
That's what we're doing. A very minuscule part of quantum mechanics. So that's what the rest of the chapter is about.
Okay.
Okay, Charlotte, I'm glad you called in today.
Okay. Thank you.
It was a pleasure talking with you. You have a good rest of your day.
Bye.
Bye-bye.